My name is Chris Alexander, and I'm the project manager for P21129 Flight Ready Heat Switch for deep cryogenic applications. Our customer, Dr. Zemkov, is interested in launching spectrometers into space on sounding rockets. In order to get the best possible set readings from these sensors, they must be cooled to incredibly low temperatures to reduce noise and any internal heat emitted from the sensor. This is accomplished by an adiabatic demagnetization refrigerator, or ADR. Our team was tasked with building the heat switch component of the ADR, which is tasked with dissipating heat from the sensor, allowing it to get to 77 degrees Kelvin. This project's focus was on designing a robust, compact, and efficient heat switch that would operate at these extremely low temperatures and survive the vibrations of a rocket launch. Thanks to designs and iterations from the two previous MSD teams, we were handed off a machined prototype. This prototype utilized a rotary solenoid, a ratchet, and a peanut cam to open and close the arms, which would then clamp and unclamp to the sensory package. Early in MSD1, our hardest team decision was whether to continue with the current design that wouldn't actuate or branch off a different route. We explored other heat switch designs, but after speaking to subject matter experts, we were advised to continue the troubleshooting and iterations of the current prototype, since it seemed very close to succeeding if COVID hadn't stopped last year's team. When troubleshooting the prototype, there were many factors contributing to unsuccessful actuation. Spring constants, coefficient of friction, and thermal contraction allowed for one factor to impact several other factors. The camshaft plate was ultimately redesigned to fit the housing better and thus reduce the amount of lateral and vertical movement. This was a big improvement and allowed the heat switch to actuate when it was assisted by a team member, as seen on the right. We believe the ceramic bearings installed by the previous team were not allowing for enough friction for the ratchet to properly index. Blue painter's tape on aluminum seemed to be right in the sweet spot for friction, which was extremely close to the friction between bronze and aluminum. As a result, bronze sliders were machined and installed. This allowed the heat switch to actuate at room temperature with reliability. The heat switch is powered by and communicates with a custom-designed PCB. It acts as both the power supply for the solenoid and a data collector, which can be used for overall system health. We were able to control when actuation occurred, for how long, and then get important feedback metrics like time per actuation, voltage, and go, no-go flight conditions. It is also streamlining the testing process for us by unifying all the different platforms we use. This project has allowed us a unique opportunity to work with liquid nitrogen and a cryostat. This has set us apart from many other groups while challenging us at the same time. Test setup and prep can take half a week and relies on many things going right. So far in testing, we have successfully actuated in a vacuum and down to 81 degrees Kelvin, as seen in this video here. We are currently experimenting with vibration testing and getting this prototype flight ready. Team P21129 would like to thank our previous teams, our subject matter expert, Dr. Zemkov, our guide, William Nowak, and supporting guide, Marty Pepe. This project would not be possible without the financial support of the RIT Center for Detectors and the use of their lab spaces. Thank you, and I hope you enjoyed watching.